Welcome to this video lecture where we continue to talk about content in the book Introduction to Nonlinear Control. And in this video, I'm going to talk about content contained in chapter 6, talking about absolute stability. So what's the motivation here? So what we've looked at so far were linear and nonlinear systems, and we have seen characterizations of asymptotic stability. We have seen a bit of controller designs for linear systems, so we can have a look at this closed loop system here. For simplicity, single input, single output linear system, where we can design a feedback gain K and design it in such a way that our closed loop system without reference signal here is asymptotically stable, has an asymptotically stable equilibrium at the origin, or then we can stabilize a reference point by selecting a different reference value here. So we have seen how to do that in chapter 3, how to design the feedback gain K here. But what is usually common in practice is that there is a non-linearity contained in this idealized feedback loop here, and we actually need to take a non-linearity here into account. One example of that non-linearity would be to say, well, our input signal, our maximal and minimal input signal are limited, meaning we can only have an input signal up to 1 or -1, but everything that's larger than that is simply cut off. So how would that be formulated? Well, there is the common saturation function in the literature, which is just Z if we are in the interval -1, 1 here, but if we are having a larger signal coming in here on the left, well, then this is simply cut off. Meaning we would like to implement an arbitrary input signal U here, but in a real application that goes through this linearity, and then the actual input that is implemented is a signal that's cut off. So that's one example of a nonlinearity that could occur here. Another one is shown through this example here, through an example of a servo valve, where we have an input U here on this side, which we can use to move this spool up and down, and then through pressure in this valve, that leads to a change here in the output Y, also moving this piston up and down. And what we can see here is that we have an overlap here, meaning if we move the spool just a tiny position or just a tiny bit, then that will not lead in a change of the output, because there is this overlap here at these positions. And that's not a design flaw, that is intentionally built so that that's not through wear and tear losing pressure there. So this is actually by design. We would like to have this overlap, but that also implies that small inputs U don't lead to a change in the output. And through a function that's characterized through the so-called dead zone, meaning around the origin here with respect to the input U, there is nothing happening. So our input U is piecewise linear, but we have this so-called dead zone around the origin. So again, a nonlinear disturbance up to some extent that impacts may impact our closed loop system, where we intend to apply in this notation here U tilde, but it goes through this nonlinearity, And then what we actually apply is this signal u of t characterized through the dead zone function. Okay, so that's just two examples of what can happen if we have some nonlinearity in our feedback loop. And this is or can be summarized through the so-called Lurie problem, where here we ignore for the analysis now the reference value, and we simply look at this feedback interconnection where we have an output y here. That output y goes through some potentially unknown function, nonlinear function depending on time, and output y, giving us the input u, and we are interested in asymptotic stability of this closed loop system for classes of functions psi. Okay, and the particular class of functions phi we are going to look at need to satisfy this so-called sector condition, illustrated through the visualization here on the right, meaning we say a nonlinearity, so a potentially unknown function phi, satisfies a sector condition if we can define parameters alpha and beta, alpha strictly smaller than beta, on a domain, so that can be restricted to the domain, such that, well, our nonlinear function lies within this sector here. The sector reduces to zero at the origin, but then allows bigger values further away from the origin, and this sector is characterized through this chain of inequalities here. Well, and that sector condition can be a local definition or a global definition. And if we look at the two functions of nonlinearities in the two examples, so if we focus on the saturation here, well, does the saturation satisfy the sector condition? Yes, it does, because we can draw here two lines, and then our sector is characterized through these parameters alpha and beta here, and we see that the saturation function is in this sector. Similarly, for the dead zone, we can look at this sector here, and again know that this particular nonlinearity is covered through this sector condition. For the sine function, that's not possible, so we can't find alpha and beta in R such that, or in such a way that we can cover it through a sector condition. Okay, well, and we have seen asymptotic stability definitions. Now we extend that to absolute stability, which is a robust stability property, and we say that our system is absolutely stable with respect to these parameters alpha and beta, again either locally or globally. If the origin of this closed loop system here now with this nonlinearity is asymptotically stable for all functions phi which satisfy this sector condition, again defined through alpha and beta. So this provides a robust stability characterization of the origin of a linear system subject to nonlinear disturbances, where the disturbances or need to satisfy a specific sector condition. And well, a couple of people worked on that and tried to come up with a characterization of absolute stability that is easily verifiable. And the first notable conjecture was the Eisenmann's conjecture. So again, looking at our linear system here with output, single input, single output, and then the statement was that this system is globally, or if this system is globally asymptotically stable for all linear feedbacks, or feedback that can be written in this way. So for all k set is in alpha beta up to some extent satisfying the sector condition, then the system is globally asymptotically stable for all nonlinearities satisfying the sector condition. So that was Eisenmann's conjecture, but it was shown that this was wrong by giving a counterexample. Then also Kalman worked on the problem and came up with a slight variation of that conjecture. So changing the condition here by incorporating the derivative of the nonlinearity, and then stating that in this case we have asymptotic stability for all nonlinearities satisfying this condition here. But again, it could be shown that this construction is not possible because there are counterexamples which satisfy the sector condition but don't lead to asymptotic stability. Well, and the actual solution that was proposed then later on is too complicated to put on in a detailed way on the slides here, but which is provided in the book, is that one criterion which combined state space methods and frequency domain methods with a visualization using the Nyquist plot, and then relying on the Nyquist plot to decide if a system is absolutely stable or not. So just a quick discussion here. So there are ways to visualize the Nyquist plot, and then to also visualize another set characterized here on the right hand side through this d alpha beta, where one can separate three different cases of what is visualization depending on the parameters alpha and beta. And then by looking at the Nyquist plots and these disks, then one can check if one of these criterion here is satisfied, allowing one to make a statement about absolute stability. A different criterion, also with the corresponding visual representation, is the Popov criterion. Again, relying on similar methods and allowing one to draw conclusions about absolute stability of a linear system subject to nonlinear uncertainties in terms of this function phi. Okay, and that concludes the presentation here, giving a quick view into absolute stability, extending the concept of asymptotic stability, and providing a robust characterization of stability of the origin of a linear system. And in the next presentation, we continue to talk about input to state stability, which is another concept of robust stability.